Hello again, and again, welcome to the channel. My effort to use a fancy drawing in the title of a geometry task failed. Still not even nearly as much viewers as I would like to see. So this time I will take the opposite approach. No drawing at all. Maybe this will gain the video popularity by its uniqueness. The conditions are quite simple. The opposite sides of a hexagon are parallel to each other, and all three diagonals connecting its opposite vertices are equal to each other. The objective is to prove that such a hexagon possesses a circumcircle. In other words, there is a circumference passing through all the vertices of the hexagon. Please pause the video, make a drawing, and think about the ways to solve the problem. Those to whom I offer the problem typically either assume that the diagonals connecting opposite vertices have a common point, or tried to prove that. In fact, this is not necessarily the case. Here is the example of a hexagon whose sides are parallel to each other. The diagonals connecting opposite vertices are equal to each other, which indeed has a circumcircle, though the diagonals have no common point. Let's remove the hexagon and rewrite the problem using mathematical notation. Phrase opposite sides of the hexagon are parallel to each other means that AB is parallel to DE, BC is parallel to EF, and CD is parallel to AF. Also, all three diagonals connecting its opposite vertices are equal to each other. So, AD equals BE equals CF. And we need to prove that hexagon ABCDEF has a circumcircle. Try to continue from here. Let's remove diagonal CF. The remaining diagonals AD and BE certainly have a common point, point K. And we draw two perpendiculars to side AB, DG and EH, where points G and H lie on the side AB. Consider quadrilateral GDEH. DG and EH are perpendicular to the same line AB. Therefore, they are parallel to each other. Also, AB is parallel to DE, which means that two other opposite sides of the quadrilateral are also parallel to each other. Therefore, quadrilateral GDEH is a parallelogram. In fact, it is a rectangle, but that doesn't make any difference, as the only thing we use here is the segment DG equals segment EH as opposite sides of a parallelogram. Now consider two right-angled triangles, triangle ADG and triangle BEH. These triangles have equal sides, GG and EH, and the hypotenuses AD and BE are equal to each other according to the condition. Therefore, triangle ADG is equal to triangle BEH, which implies that the acute angles in this triangle, angles DAB and EBA, are equal to each other. Now let's simplify the drawing and refer to triangle AKB. This triangle has two equal angles, DAB and EBA. Therefore, it is isosceles. KA equals KB. We can write the equalities for the lengths of complementary segments. The length of KD equals the length of AD minus the length of KA, and the length of KE equals the length of BE minus the length of KB. But the length of AD equals the length of BE, and the length of KA equals the length of KB. Therefore, segments KD and KE are equal to each other. Now we can restore diagonal CF, meeting the other diagonals AD and BE at points L and M respectively. We can consider parallel lines AF and CD, along with equal diagonals AD and CF, and prove in a similar way that LC equals LD and LF equals LA. Finally, we can consider parallel lines BC and EF with equal diagonals BE and CF, and prove that ME equals MF and MB equals MC. The last 6 equalities is all we need for the rest of the video. So let's copy them to the new page and start with a simple case when all the diagonals meet at a single point. We can interpret that as 3 points K, L, and M merged into a single point, point O. So we can replace all letters K, L, and M in the equalities by letter O. This gives 6 equalities relevant to the current case. So let's move them above and start uniting them into a long equality. We have OA equals OB. Let's copy that. We also have OB equals OC, so we can extend the equality. Next, OC equals OD, so our equality continues growing. Now looking for OD equals OE, here it is, and one more term in the equality, OE equals OF, which makes all the vertices of the hexagon involved. One of the original equalities happened to be redundant, but that's not a problem at all, given that the long equality clearly shows that point O is equidistant from all the vertices of the hexagon ABCDEF. If R is the distance from point O to each of the vertices, then the circle with center in point O and radius R is the circumcircle of the hexagon ABCDEF. Now to non-trivial case, when points K, L, and M are distinct. Let's draw the bisector of angle AKB meeting side AB at point P, while Q is the point where the continuation of the bisector meets side DE. Since triangle AKB is isosceles, the bisector KP of its apex K is the perpendicular bisector to the base AB. Near point K, there are two pairs of vertical angles. Angle DKQ equals angle AKP, and angle EKQ equals angle BKP. Since angles AKP and BKP are equal to each other, then angle DKQ equals angle EKQ. In other words, KQ is the bisector of angle DKE. But angle DKE is the apex angle in isosceles triangle DKE. Therefore, KQ is the perpendicular bisector to the base DE. Note that segments KP and KQ form a single segment PQ. So we can combine the statements about KP and KQ into a single statement. PQ is the perpendicular bisector to sides AB and DE of the hexagon ABCDEF. Now let's draw the bisector of angle KLM, meeting side CD at point R. And let S be the point where the continuation of the bisector meets side AF. Using isosceles triangles DLC and ALF, we can prove that RS is the perpendicular bisector to sides CD and AF of the hexagon ABCDEF. And we also draw the bisector of angle KML and extend it beyond the vertex M. This gives two new intersection points, point T on side EF and point U on side BC. And again we have two isosceles triangles, triangle EMF and triangle BMC. And we prove that TU is the perpendicular bisector to sides EF and BC of the hexagon ABCDEF. Now, the culmination part of the proof. All three bisectors in triangle KLM meet at a single point, point O. Since we no longer need the equality in the box, let's wipe them out and see what we can write instead. Point O belongs to segment PQ, and segment PQ is the perpendicular bisector to sides AB and DE. Therefore, point O is equidistant to endpoints of side AB, segment OA equals segment OB, and point O is also equidistant to endpoints of side DE. Segment OD equals segment OE. Also, point O belongs to perpendicular bisector RS, to sides CD and AF. Therefore, point O is equidistant to the endpoints of these sides. Segment OC equals segment OD, and segment OF equals segment OA. Finally, point O belongs to perpendicular bisector TU, to sides EF and BC. And we complete the box with equalities. Segment OB equals segment OC, and segment OE equals segment OF. Now the box contains the same equalities as we had in the previous page. Only the drawing changed, because now the equalities apply to the general, non-trivial case. And again we write the long equality. OA equals OB equals OC equals OD equals OE equals OF equals R, which shows that point O is equidistant from all the vertices of the hexagon ABCDEF. So, the circle with center at point O and radius R is the circumcircle of the hexagon. And this is the end.